For example 3, we want to find the equation of a plane through the point P negative 4, 0, 2 that is perpendicular to the line r of t equals 2t, 5t minus 1, and negative t plus 3. Now let's think about that for just a second. So you have some line, call it r of t, right? Some vector valued function line. There are lots of planes that would be perpendicular to that, right? So there are infinitely many planes that would be perpendicular to it. And we want the one that contains the point P. I probably drew that too large, but here's point P right here, which of course is x0, y0, z0. Now, if you're thinking what I'm thinking, right, they said they want r to be perpendicular, so isn't r really in the direction of n already, right? Because n, which is the direction vector piece of this, so if I make n, forget about the point part, and I just say it's 2, 5, and negative 1. That's the direction vector piece of this. So 2, 5, and negative 1, that is the direction vector that is automatically perpendicular to the plane because it's established ahead of time. Here, let me. Right? So you're saying, hey, there's stacks and stacks and stacks of planes that are perpendicular to this, right? So if I have my n right here, which is the direction that this is heading, and I say, okay, n is here, that's some component of the r of t. Because, of course, the vector, the n part is free, so I can put it wherever I want, right, because it's a direction vector. So I can say, okay, well, that piece of it, that direction portion of it, forgetting about the negative 1 and the 3, that will automatically be perpendicular to the plane. So I have my n. I have it because they said they want this equation of the plane perpendicular to this line, right? Well, then that's my direction vector, period. That will be the normal piece, right? It's perpendicular. And then I will just use my point, and it's done. Simple as that. So I'm going to take 2 times x minus something, give me 1 second, and then plus 0 times, not 0, 5 times, I was looking at the 0 there, y minus 0, actually I can tell you what that one is, and then minus 1 times z minus something will be equal to 0. And then you're just going to put in those values. So it's a plus 4 because it's minus a minus, so it's plus 4. And then 0, and then 2, like that. By the way, if you haven't gotten into the habit, you do want to make your z's and 2's look different. Otherwise, it can be very confusing for you in Calculus 3 because we use z's all the time. So when I got into Calculus 3, I started learning to put slashes through my z's because otherwise they look too similar for me. So that is a perfectly acceptable equation of the plane. It's a little bit of a cheat of a question because you don't realize how simple it is, right? And it's because they say it's perpendicular to this line, so therefore that direction vector that comes from that line is normal, orthogonal, perpendicular to the plane. And so you just use it. If you want to simplify that down, of course, you can write it as 2x plus 5y minus z. See, that'd be 8, and then 2, so that's 10. So equals negative 10. All right, for the next example, we're going to find the equation of a plane that goes through the point P, which is 5, negative 4, 2. So, of course, that's an x0, y0, z0, as per usual. But it's parallel to this plane, which is negative 3x plus 7y minus z equals 4. Now, since they're parallel, since these two equations are parallel, that means that the n is going to be the same for both equations. Nice. All right, well, let's see here. I have one plane, plane number 1, down here. I'll call this plane 1. And then I have another plane, plane number 2, up here. I'll go up here. And they're parallel. And since they're parallel, that means that the n has to be the same for both. And of course, vectors are free, so as long as it has the same direction, it doesn't really matter that it's floating in a different spot. And of course, it would be perpendicular because it's an n, it's a normal vector, right? So it's orthogonal to the plane. All right, so now where am I going to find what n is? Well, you actually already know what n is. So if you look over here at this equation of the plane, oh, that should actually have been one of the planes. So I'll call it plane number 1. There we go. So we'll call this plane 1. Right? Well, look at it. You can see that it breaks down, and the direction components are -3, 7, and -1. So if that's plane 1, I know that this right here is -3, 7, and -1. And so then this other plane, the plane I'm looking for, has my point P sitting on it, right? So there's point P right there, sitting on my plane. And I want to find the equation of this plane. But they're parallel, so they're going to have the same, although they're supposed to be parallel. Mine look a little wobbly, but they were supposed to be parallel, right? If they're parallel, then that means that that normal vector that I found from this, right, it's right here, -3, 7, and -1, those 3 components are going to be the same. So this is also going to be -3, 7, and -1. All right, well then that means I know my equation of my plane. So plane number 2, which is the one I'm actually looking for, is, now let's see, -3 times x minus 5, right, because that's my x0, plus, and then 7 times y minus -4, so that's really y plus 4. And then minus a 1, so minus 1 times z minus 2 equals 0. That is the equation of that plane, the new plane that's parallel to the old one, which is right there. All right, and then if you want to write this out a different way, of course, -3x plus 7y minus z equals, let's see, that's 15, 15 and 28, and then another 2, so that's 45, right? So that equals -45. And just for fun, so you can see it, I did graph them both in Maple, so you can see that they are parallel. So we have plane 4A right here, which is the given plane, and plane 4B, which is right here. And then I just told it to implicit plot both of those in brackets, and then told them to use different colors. I originally told it purple and blue, but it just didn't look good. So I switched it to green and blue so you could see they are indeed parallel, those two planes. It's getting cut off over here just because of my XYZ limitations, but you can still see how it's supposed to look. So for this next example, we want to find the intersection for the planes x plus y minus z equals 1 and x plus y plus z equals 1. Now for starters, you can tell they intersect because they do not have the same direction vector at all, right? So we know that they are not going to be parallel. In fact, we can make a note of that. So note the direction vector on this one is 1, 2, -1. And the direction vector on this one is 1, 1, 1. So they're not parallel. If I want to think of this as like direction vector 1 and direction vector 2. They're not multiples of each other. These are not parallel planes. All right, so then let's get rid of one of the variables with algebra, right? Because we need 2 points to make a line. So we need to find a couple points so that we can do this. Right, so just a reminder, we need 2 points to find that line. Okay, so I'm going to take the first equation, x plus 2y minus z equals 1. I'm going to add to it the other equation, x plus y plus z equals 1. In other words, I'm using elimination. I'm using algebra here. So 2x plus 3y equals 2. So now I'm going to find some points that satisfy that equation. And then, well, I'll find a couple values, and then I will substitute back and find the z value. So let me see here. Let me let, for point P, I'm going to let x be equal to 1. Now, you don't have to pick 1. You can pick kind of anything. It doesn't really make any difference. If I let x be 1, then 2 times 1 plus 3y would be equal to 2, right? So therefore, 3y would be equal to 0, which means y would be equal to 0. So I know that the point is 1, 0, and then to find the z value, I have to go back up to the originals, either one of them, because technically this line should be on both points, or both planes. So then I would say, okay, well then, I know x plus y plus z equals 0, so, excuse me, equals 1. So if I know that this is 1 and this is 0, that means z is equal to 0. So I have a point P now, which is 1, 0, 0. And then I'm just going to pick something else, right? So for let Q, you can kind of pick whatever you want. I'm going to let x be equal to, I don't know, 3. You could let it be 0. You could let it be 2. You just can't do 1 again. But let me see what happens if I choose 3. Well, here, it doesn't make any difference. I'll do 0. That's more likely what you would think of. All right, so if I choose 0, then I know Q is going to be 0, something, something. So now I go back into this equation here to figure out what y would be. So I'd say, okay, well then 2 times 0 plus 3y equals 2. So that means that y is 2/3. All right, and then if I let y be 2/3, then I know that, let's see here, x plus y plus z is equal to 1. So 0 plus 2/3 plus z is equal to 1. So therefore z must be 1/3. Sorry, my phone rang there. All right, so this is 1/3 right here. All right, so now I have a point P and a point Q. How is this helping? All right, well, let me just make a little graph here. So I have one plane kind of doing this, and I have another plane intersecting with it. Right? And they're intersecting at a line. And I'm looking for the equation of that line. I know I have a point P that's on it, and I know I have a point Q that's on it. So basically we just found 2 of the points that are on that line. Of course, there are lots more. And you just pick randomly, pick a value that you think might be nice, or, something like that. All right. Now, how in the world is this going to help me? Well, I know that my direction vector on this plane. So if this one is x plus y plus z equals 1, and this one up here is x plus 2y minus z equals 1. There we go. So I've got my 2 planes, right? Plane 1 and plane 2. I know that the direction vector between those 2 points, P and Q are on that line. So if I can find the direction vector between the 2, then I'm golden, because I have what I need in order to come up with the equation of the line. So the direction vector, I'll just call it V, would be from P to Q, or from Q to P. It doesn't actually really make any difference. So if I go from P to Q, that's terminal minus initial. So 0 minus 1 is -1. 2/3 minus 0 is 2/3. 1/3 minus 0 is 1/3. There's the direction vector of my line. And so that means that the equation of the line, remember, the equation of a line, R of t, is equal to my direction vector times t plus my point P, right? Well, OP, if you want to do it that way, from the origin to point P, which I did because I already turned it into a vector. All right, so that would be this direction vector, V. You call it D for direction, whatever makes you happy. So it'd be -1 2/3, -1 2/3, 1/3 times t plus OP, which is 1 0 0. Like that. There, I was unhappy with my color choices, so I fixed it. All right, so that would make it -t. So if you're going to write this out, it'd be equal to -t plus 1 plus 1 and then 2/3 t plus nothing, right? 2/3 t plus 0, and then 1/3 t. Again, plus 0. So that is the vector valued function for the equation of that line right here. So it's a little bit strange, but bear with me here. I'll go over the process one more time. You take the two equations and you use algebra to eliminate a variable. That's what I'm doing here. To eliminate, and this one just eliminated z automatically when I add them up because one was a minus, one was a plus. Otherwise, you're going to have to manipulate these equations to make it so that one of your variables goes away. Oops, I eliminated z in this one, but it might not always be z, so I'll just say a variable. That gets you this new equation right here. And then you use that and you use the original equation. So you just pick some random x's, kind of anyone will do. So you pick an x, then you find the y from this equation right here, and then you find the z from the original equations back up there. Either one of those original equations should work. And then you do it again for another point. Pick a random x, use that equation with only two variables to find the other variable, and then go back to one of the original equations to find the third variable. And then once you have those 2 points, you make a direction vector from those 2 points. And that's direction vector times t plus OP, right? The origin to one of the points that you found. And I did graph them in Maple just so you could kind of see what you're finding. You're finding the equation of the line where the two planes intersect. So you can see they do have an intersection, and you're finding that equation of that line right there. But in 3 space, of course.